section, please record it. Right. Okay, thank you. Right. So previous class we discussed that. So all these things are over. So now we will see the harmonics, this unipolar PWM technique. This is also we discussed. And this is the same alternative implementation of unipolar sine PWM technique. So this is the corresponding harmonic spectrum, the corresponding harmonic spectrum for unipolar sine PWM, unipolar sine PWM. So here also we assume that MF is 15, right? So here also this MF is 15. So if you notice that, so this is 15, right? This is 15. Somewhere you have this 15, right? So corresponding to this 15, so there is no harmonic, right? That's entire harmonics are not present, but you have harmonic at 2 MF. This is corresponding to MF. This is 2 MF. This is 3 MF, and this is 4 MF. Right? So corresponding to this MF, there is no harmonic. Similarly, corresponding this 3 MF, we have no harmonic, right? But at 2 MF, exactly at 2 MF, that is corresponding to 30, you have no harmonic. Similarly, corresponding to 60, you have no harmonic, but these sideband harmonics are present. So these sideband harmonics are present. Right. So that means you have harmonic at 2 MF plus or minus 1, 2 MF plus or minus 3. Right. And you have this 4 MF plus or minus 1, plus or minus 3, plus or minus 5. Similarly, 6 MF plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 7. So likewise. Okay. So completely these harmonics, that is even multiple, means odd multiples of MF, are completely eliminated. Right, completely eliminated. So now the lowest order harmonic, right, in case of is MF, so what is the lowest order harmonic? So if you consider MF equal to 15, right, so what is this corresponding harmonic? 2 MF minus 3, so that is 27th order harmonic. Yes, we have this 29th order harmonic, and we have this 31st order harmonic, and you have this 33rd order harmonic, right? Okay. Similarly here, you can write down, right? Okay. So first thing is, so why this MF, 3 MF, 5 MF, all these harmonics are eliminated? So that we will observe right first. Okay. Right. So this is the output voltage. So this one is the output voltage of the corresponding unipolar sine PWM method. So if you notice that, so here, so we already discussed that you have 15 pulses here, and here another 15 pulses, right? So that effective pulse number in one cycle is increased to 2 MF, right? The effective pulse number is increased to 2 MF. So that means, the meaning is, if bipolar, right, if bipolar, for example, if it is operated at 1 kHz, right, the same one at the same, right, the same carrier and same modulator is unipolar, right, it is effectively operate at 2 kHz. It is effectively operate at 2 kHz. Clear? That unipolar is effectively operating at 2 kHz. It's clear? So unipolar is effectively operated 2 kHz. So that means, so here in case of bipolar, so we all, if you calculate, if you sum all these, right, so this is 15 pulses, Okay, this is 15 pulses. So that means the effective, the switching frequency, that means each switch, right, is operated for each switch, right? You have 4 switches, right? So each switch is operated for how many times? So here this is corresponding to, these are the gate pulses, right? So this is corresponding to S1, S2, and this is corresponding to S3, S4 in case of bipolar, right? So that means each switch, if you count all these, right? So that is 15 times. Similarly, this bottom ones, if you count all these, so this is 15 times, right? So that means each switch is operating for 15 times. So that is device switching frequency, device or the switching frequency, right? The device switching frequency is equal to the carrier frequency. Clear? Right. The device switching frequency when you are using bipolar sine PWM, so that is equal to the carrier frequency. Clear? Similarly, you have inverter switching frequency, right? So that is also equal to the carrier frequency. So this is also equal to carrier frequency, provided all these are, that means MA modulation index is less than or equal to 1. Okay, we'll discuss this, why it is like this. Okay, so here in case of bipolar, the device switching frequency and the inverter switching frequency, we have two terms. One is device switching frequency. So that means at what switching frequency the devices are operating, right? That is one thing. And you have another one, that is inverter switching frequency. That means at what switching frequency the inverter, or effectively that inverter is operating, right? In case of bipolar, both are same. So therefore, in harmonic spectrum, you have harmonics at MF and you have harmonic at 3MF. You have harmonics here and you have harmonics here, right? Clear? So in case of unipolar, right? In case of unipolar, the device switching frequency, right? If you count all these, right? Okay, if you count all these things, so this is 15. So this is also 15. The device switching frequency is equal to the carrier frequency. So that means each device is operating for carrier frequency, but the inverter switching frequency is 2 times the carrier frequency. Clear? The effective switching frequency of the inverter is 2 times the carrier frequency. So that is the main difference. Okay, so therefore, right, see here each device is operating at the carrier frequency in both unipolar and bipolar case, right? But effectively that inverter frequencies, in case of unipolar, it is doubled, right? So therefore inverter is effectively operated multiples of the MF, right? So therefore, so this means the inverter effect, that means the harmonics will start at 2MF onwards, right? So you know that, right? At 2MF, exactly 2MF, 4MF, 6MF, exactly at those frequencies, the harmonics will not present, right? So therefore you have left with 2MF plus or minus 1, plus you are left with this one, and this one, and this one, and so on. Is clear?
Yes, sir.
Right. So now what should be the value of MF? Whether it will be even or it should be odd. In case of bipolar, we discussed that MF should be, in case of bipolar, MF should be odd, right?
Odd.
Okay, in case of bipolar. In case of unipolar, what it should be? It's an even number or odd number? In case of bipolar, sorry, in
Odd,
case
sir.
of unipolar,
Odd.
Odd.
odd number or anything?
Anything is fine.
Anything is fine, right? So you have this 2MF, right? 4mf and 6mf, so that means it should be anything, right? Okay, it may be even number or it may be odd number. Okay, so to eliminate even odd harmonics, in case of unipolar, you can select anything, right? It may be even number or odd number, but in case of bipolar, it should be odd number. Clear? Right. And there are two types of there are two types of PWM methods. One is synchronous PWM and asynchronous PWM. Okay, one is synchronous PWM and another one is asynchronous PWM. So meaning is, right, so meaning is, if you notice this, I'm doing it. So if you notice that you have this modulating signal, right? You have this modulating signal and you have this carrier signal. Okay. If you observe that, so both are started at 0, right? So that means PWM signal, that means modulating signal and the carrier signal, so both are synchronized. So that is known as synchronous PWM. So when it is asynchronous means when the modulating signal is 0, right? So that means carrier may be started with something else, right? Okay, so that is known as asynchronous PWM. Okay, it's clear? Asynchronous and asynchronous. In case of asynchronous, right? In case of asynchronous, okay, just keep remember that we'll discuss in the next one, right? So you know the difference, right? Synchronous and asynchronous. In case of synchronous, right? So both modulating signal and carrier signal are started at same position, right? So this is about unipolar and bipolar, right? So when you compare this unipolar and bipolar, the first thing is the effective switching frequency of inverter is doubled in case of unipolar, and another one is dV by dt across devices. Voltage stress or dV by dt across devices. So that means here in case of unipolar, so this is the transition. So that means the voltage is changing from VD to 0 and 0 to minus VD, right? 0 VD to 0 and 0 to minus VD. So that is the stress. So that device must be withstand for that, right? In case of bipolar, right? In case of bipolar, the voltage is plus VD and it is directly jumps to minus VD, right? It's plus VD and this is minus VD, right? So that means if you compare the voltage stress or dV by dt, so here it is doubled. Okay, it is 2 times whatever the dV by dt or voltage stress, so that is available to unipolar. Okay, so voltage stress is increased in case of bipolar. So normally this bipolar scheme is not preferred. This bipolar scheme is not preferred, especially it is having some applications, especially in MPPT. Right, MPPT. You know what is MPPT, right? Maximum power point tracking, especially used in PV applications. We have some specific advantage in PV applications that I will discuss in later classes. Right, you just keep remember that. So normally bipolar sine PWM is not preferred method, right? Okay, generally unipolar is preferred because of increased harmonic performance and reduced dV by dt. Okay, so only in general PV applications there is a special case in PV applications that we will discuss in later classes, right? Okay, this is about unipolar and bipolar. So next
Sir,
we move to the three
hello.
phase. Yeah.
dV by dt is more or less in case of bipolar.
In case of bipolar, it is more, right?
Yeah, you just told it is less.
Maybe you're okay. In unipolar, it is less, and bipolar, it is more. Okay, it is 2 times. Okay, clear?
Yes, sir.
So next we move to three phase. Right. So next we'll move to three phase. Right. So in case of three phase, there is nothing like unipolar or bipolar. In case of three phase, there is nothing like unipolar and bipolar. So only one method is there. So only one method is there, right? Okay, this is three phase implementation. In three phase, you have three phase legs, right? You have three phase legs in three phase. So here you require one carrier. You require one carrier and three modulating signals. You have three modulating signals. You have switches here like this, right? You have one. So you have switches S1, S3 here, and S5. Similarly, this is S4, S6, and S2, right? So this is three-phase inverter, right? So this one will compose one phase leg. So this one will compose another phase leg, and this is another phase leg, right? So this is A phase, B phase, and this is C phase. Okay. So you require one carrier and three modulating signal. So here each modulating signal will control one phase leg, right? So that means you have three modulating signals. So these modulating signals are shifted by 120 degrees. Okay, these modulating signals are shifted by 120 degrees. So this can be defined something like this: VMA. So that is VM sine omega t, right? VM sine omega t, for example. So next one, VMB is shifted by 120 degrees, and VMC. So this is again another shifted by another 120 degrees, right? So here this is A phase. For example, if you assume this is A phase modulating signal, right? And you have this B phase modulating signal, and you have this C phase modulating signal. Okay. So A phase modulating signal only controls S1 and S4. B phase modulating signal will control S3 and S6, whereas C phase modulating signal will control S5 and S2. Right. So each modulating signal will control so different phases. Okay, but the carrier signal is remains same. The carrier is remain same. Okay, so this is same thing, right? In case of three-phase inverter, right? When the upper switch is on, okay. So this is three-phase inverter, right? So this is positive DC bus, and this is a negative DC bus. This is positive DC bus and negative DC bus. So we are actually measuring voltage VAN, right? So A phase corresponding to this negative DC bus, right? So when this upper switch is on, so this voltage is VS. When S1 is on, so voltage VAN. So but between these two voltages, so that is plus VS. So when this bottom switch is on, so that is 0. You have two voltage states, either VS or 0, right? So that is already, we already discussed it, right? Okay. So here, okay. So this one is comparison, this VAN, right? So this is A phase modulating signal is compared with the carrier signal, A phase modulating signal is compared with the carrier signal. Similarly, this is B phase modulating signal is compared with carrier signal. B phase modulating signal is compared with carrier signal, and we have this VAB, so that is VAN minus VBN, right? We discussed this, right? So here VAB is the subtraction of these two, so we need to directly subtract this VAN and VBN, so you will get this kind of pulse. Okay, this is what similar to what we studied for unipolar. Okay, each the difference of two pulses, right, will split into two, right? So this is a VAB line voltage. Clear? Right. It's clear? So you require three modulating signals, right? The same thing, right? I think just a moment. Right, this is not required. Yeah, this is the corresponding harmonic spectrum, right? So this is the corresponding harmonic spectrum for considering MF equal to 15. So this is the harmonic spectrum considering MF equal to 15. So here you have no harmonic at MF, 2MF, 3MF, or any MF, right? You have no harmonic here, but you have harmonics, so that is MF plus or minus 2, 2MF plus or minus 1, and you have harmonics at 3MF plus or minus 2 plus or minus 4, and similarly you have 4MF plus or minus 1 and plus or minus 3. So this is the harmonic spectrum, so that it will follow. Okay, this is the harmonic spectrum for sine PWM technique, right? You have no harmonic at MF, 2MF, 3MF, or 4MF, so but only you have this sideband harmonics. For example, if you consider MF equal to 15, so this is 13th order harmonic and this is 15th order harmonic. Okay, similarly this one is 29th order harmonic and this is 31st order harmonic. Clear?
Sir, actually the 29th and 31st order harmonics won't be greater in magnitude, right, sir? In general.
In general?
The magnitude of the 29th and 31st harmonics will not be greater than the 13th and 17th, right, sir?
That all depends on no, here it will be greater than that one. Okay, why? Because see, if you notice that, see here how many pulses here, this is 3 phase, right? So here this pulses number is also effectively doubled, right? Okay,
Yes, sir.
so in this pulse number is also effectively doubled, right? So therefore, so here normally this this is greater, this 2MF is normally greater than this 2MF plus or minus 1. Okay.
Oh, okay, sir.
So now, so we already discussed this, right? Synchronous PWM and asynchronous PWM, right? Okay. So now you have three modulating signals. You have three modulating signal and one carrier, right? Okay.
Excuse
so
me,
that
sir.
means, oh yeah.
Sir, how we will get to know, sir, ki which amplitude, which harmonic amplitude is greater or lesser, sir?
So that is only you have to use FFT analysis only. Okay. Right. So you have to use frequency, a fast Fourier analysis. So then only you can know so which harmonics are cancelled. Okay, we will discuss that. So by using this double Fourier series, we have to do that. Okay,
Okay,
we'll
sir.
discuss that. You just remember that. Okay, right.
Okay, sir.
Actually, double Fourier series is very complicated one. So at the beginning, if I start with that, right, you'll fed up and right. Okay, so that's why it's slowly moving. We'll review all these things you have studied, right? We'll review all these basics. Okay, after that, slowly we'll jump to the actual subject, right?
Okay, sir.
Okay, how these things you will obtain this, either you can simulate, if you simulate this one in MATLAB, and if you observe the frequency spectrum, right? So all these things you can obtain. Okay, so if you want the derivation, so in that case you need to use a double Fourier series. So you have Fourier series, right? When the waveform is periodic, you normally we use a Fourier series, right? When you have something like some train of pulses, we normally use this double Fourier series. Okay.
Sir. Yes,
So
sir.
just remember that for time being. So these waveforms are normally just obtained from some simulation, right? Okay. Clear? So now we discussed synchronous and asynchronous PWM. We discussed synchronous and asynchronous PWM, right? Okay. So that means meaning is, okay, meaning is so meaning is, for example, so if A phase, it starts, for example, you have this A phase, right? So A phase modulating signal, it starts from 0, right? It starts from 0. At the same time, that carrier is also 0. Okay, right? So that means A phase and B phase are going sinusoidal, right? Means synchronous, right? In case of B phase, right, you have this B phase modulating signal. So if it is 0, right, at the same time, we are expected that this carrier is also 0. Okay, so that means if A phase is start from 0, the carrier is also start from 0. So that means B phase start from 0, the carrier also start from 0. Similarly for C phase. Okay. See here, right? See here, this A phase is start from 0, right? At the time the carrier is also 0. So somewhere you have this B phase, right? You have this B phase, and here you have this C phase. Okay, clear? You have this A phase, B phase, and C phase. So all are synchronized with the, someone has turned on the mic, please turn it off. Okay. So this A phase, B phase, see here, this is carrier, right? So this is carrier. So this carrier is like this carrier is like this, right? So that means A phase, B phase, C phase modulating signals are synchronized with the carrier. Got it, right? So when A phase modulating signal is 0, the carrier is also 0. So here also carrier is also 0 and going negative. So here also carrier is 0 and going negative, right? So such kind of PWM scheme is known as synchronous PWM, right? In case of asynchronous, right, so that is not, if it is 0, it may be some other value in case of B phase, right? So now the point is, or now the question is, what should be the value of MF? What should be the value of MF, right, to obtain this synchronous PWM? It should be multiple by which number?
120.
Right. So for example, if I select MF, right, MF equal to 21, right? So that means, for example, if I select 1050, right? So it should be, that is carrier frequency. So it should be divisible by 3. So then only, so this will happen, right? Agree? So that means from here to here, right, it is full cycle, right? From it is full cycle, you have this 21, right? So this is, again, you have this A phase is starting here, right? Okay, so this is A phase, this is B phase, and this is C phase, this is A phase, right? This entire thing, you have this 21 pulses, right? So from here to here, you have 7 pulses, and here to here, you have 7 pulses or 7 carriers, right? So that's why it is synchronous, right? Clear? To have this synchronous PWM, right, this MF should divisible by, this MF should divisible by 3. Right, this MF should divisible by 3, so then only it should be a synchronous PWM. You got it? Clear? Is clear?
Yes, sir.
Okay.
Yes, sir.
Okay, it should be divisible by 3, so they have some synchronous PWM, right? So now what is the advantage with synchronous PWM means, right, when you have synchronous PWM, there is no here, if you observe here, right, so these are almost 0, right? So practically these are some minute values, so that's almost 0, so that is present. In case of asynchronous, we have some values, right, we have some random values or some small magnitude will appear here, right, or some interharmonics will appear. Interharmonics will appear, so when it is asynchronous PWM. Okay, so when it is synchronous, so we'll get a clean waveform, so that what I shown earlier, so that means harmonic at MF plus or minus 2 to MF plus or minus 1, so something like that. It follows some pattern. So in case of asynchronous PWM, right, in case of asynchronous PWM, some small, right, some small lower order harmonics or interharmonics will appear, so their magnitude is small, so but still if you select properly MF, so that can be also eliminated, right? Okay, so in case of this three phase, this MF should be even or odd. MF should be even or odd in case of three phase.
Divisible by 3.
So in case of three phase, right, so in case of three phase, this MF should be odd, right, and divisible by 3. Okay, this MF should be odd and divisible by 3. Clear? So that means we need to select a number, something like 21 and 27, right, 33, something like that, right? Okay, you should not select 20, that is even number, right? And moreover, it is not divisible by 3, right? So when you have this three phase, this MF should be odd and it should be divisible by 3. Okay, clear? So remember one thing, so when MF is greater than 21, right, when MF is greater than 21, synchronous and asynchronous, so both are more or less same. Okay, synchronous PWM or asynchronous PWM, so both are, that means more or less the performance is same. Okay, so still some harmonics will present, so but their magnitudes are very less. Okay, so if you have MF, if you choose to MF should be less than, if you choose MF less than 21, so then you have to make sure that it must be a synchronous PWM. Okay, if it is greater than 21, right, you're not worried that much about whether it is synchronous or asynchronous. Clear? It's clear? So you have any doubts on this?
Sir, it is a three phase. That's why you are saying that it is divisible by 3.
Mm-hmm.
For a what you told is for a synchronous PWM, MF
Yeah.
should be divisible by 3.
Yeah. Okay.
This is because of three-phase system.
Because of?
Three-phase system.
Yeah, because of three-phase system. Okay. So this is about three-phase PWM, right?
Okay, sir.
In single phase, right, you have one carrier and one modulating signal, right? So normally that synchronous and asynchronous concept will not come, right? Okay.
Okay.
In single phase, when you have, if you have bipolar, you have one modulating signal and one carrier signal, so that concept will not come, right? So this is normally comes in single three phase.
V shape. So there also we use the V shape and inverted V shape.
So obviously both will be same, right? Okay. So here, so both are inverted, right? So obviously it is synchronized.
Okay.
Okay. Obviously it is synchronous, right? So this is normally occur in three phase. Okay.
Sir.
Yeah.
Sir, in case of single phase, in both case unipolar and bipolar, sir, MF should be
Okay.
even for existing the harmonics, sir.
MF should be
Even.
means I'm not getting your question.
Sir, that in case of bipolar sine PWM, sir, we have written, sir, that if MF is equals to even, then harmonic will exist, sir.
MF
So
is even.
Yes, sir. Then a harmonic will exist.
No, you're not getting the point. So MF should be odd, right? MF should be odd. We need to select MF as an odd number so that you can eliminate the even order harmonic. Okay? Clear?
Yes.
So we need to select the MF as a odd value so that the even order harmonics are eliminated. Okay? So that is the point. Okay?
Yes.
So we never completely eliminate all the harmonics, right? Some harmonics will present, so based on the spectrum, right? So here it is difficult to handle, or it is both. If it means when compared to odd order harmonic and even order harmonic, so even order harmonics are more dangerous when compared to odd order harmonic, right? So even order harmonic will normally induce some DC offset. So all these converters are fed to a transformer, right? So when you give some DC offset to a transformer, what could be the resultant? So it will change the flux waveform, right? And the magnetizing current it increases, and the flux and the magnetizing current it will increase, and the flux maybe means the transformer core may be saturated, right? So to avoid all these problems, we normally eliminate these even order harmonics. So we need to carefully select to avoid that, right? Clear?
Yes, sir.
You have any other doubts?
Sir, actually, as we go for higher order, higher phase systems like 5 phase and 7 phase, we'll be having that divisibility change like equally. Like for 5 phase, we need it to be divisible by 5 or something like that.
Yeah, it should be divisible by 5, right?
Huh.
In 5-phase system, that angle is 360 degrees by 5, right? That means 70 degrees phase shift is there, right? So it
Yes,
should
sir.
be divisible by 3. But the meaning is, the thing is that when it is MF is greater than 21, right? So normally we
Yes,
not
sir.
worry that much about whether synchronous or asynchronous, right? Okay.
Yeah, okay.
Okay, I'll move forward. So next one is over modulation. So over modulation, right? So previous case, right? So previous case. So for example, this carrier are ranging from +1 to -1, right? Carrier are changing from +1 to -1. So this modulating signals, so this is having some peak value, right? So this is also having some peak value, right? So we assumed that, so that peak value is within the limits of +1 to -1. So that means we assume that the peak value is within the limits of +1 to -1, right? So here this is over modulation. So that means, so this magnitude is greater than, so that means it is greater than, right? Clear? So now what will happen? So this modulating signal is greater than the actual carrier signal. So that means it is exceeded 1. So in this case, so this MA is, the peak value of this is around 2, right? And its peak value of the carrier, so that is 1. So MA is 2 here. So MA is 2 in this particular case. That is also what I mentioned. MF is 15, right? So what is the here? What is the advantage? What is the thing here? So here this is the intersecting point with carrier 1, that is A phase, and this is B phase. So here there is a direct intersecting from here to here. So there is no intersecting point, right? So therefore, a large pulse is appeared here. Okay, a large pulse is appeared here, right? Clear? So there is no intersecting point from here to here. So therefore, a large pulse is appeared here, right? Clear? So earlier you have these, right? Because of intersecting points. So now there is no intersecting point with the carrier and the modulating signal. So therefore, directly you'll get this bigger pulse, something like this, right? Okay. So the advantage with this one is, right, the advantage with this one, so if you compare this one, so where the waveform is, you have pulses here, and so instead of this big pulse, so this RMS value is increased, right? So this RMS value of the output voltage is increased. Agree? So why the RMS value is increased? So earlier you have some pulses, something like this, right? Some portion of these are removed. So that means RMS value is reduced. So now instead of that, you have this bigger pulse. So therefore, the RMS value of the output voltage is increased. Okay, the RMS value of the output voltage is increased. Clear? So by going over modulation, the RMS value of the output voltage increased. But the disadvantage with this is, what is the disadvantage with this is, right? So here, so there is no, it is not forming any intersecting points, right? So that means the switching frequency of the inverter is reduced. So therefore, you will get some lower order harmonics. Okay. So the intersecting points are reduced. So therefore, you will get some lower order harmonics. So you will get some lower order harmonics. Clear? By using over modulation, right, the RMS value of the output voltage is increased. The RMS value of output voltage is increased because it is making a lesser number of intersecting points. So therefore, it is increased. And the disadvantage is, so it will induce some lower order harmonics, right? It will induce some lower order harmonics, right? Clear? So now, so for example, if I keep on increasing this MA, now it is 2, right? So now it is keep on increasing, and now I increase it to 3 or 4, right? So what will happen if I increase it to higher number, right? So instead of that, you will get one bigger pulse, right? If you keep on increasing the modulation index, you will get some single pulse, right? So here you may get some, instead of that, you may get some larger pulse, something like this, right? Okay, you'll get something like this, right? The pulse is induced, right? Okay, clear? So now, when the pulses are reduced, this harmonic, it will further increase the lower order harmonics. Clear? So based on that, so once if we keep on increasing, right, so the output voltage will not further increase, right? Once it is making some intersecting points here, right, it will not make any other intersecting points, right? So that means the output voltage will be saturated. So based on that, so we divide into 3 groups or 3 parts. So this is corresponding to MA. I will draw. Let's see.
Sir,
Yeah.
sir, while lower outer harmonics are increasing,
See, earlier the waveform is something like this, right? Okay. Something like this, right? Okay. So this is the waveform. So in that case, so now what will happen? The intersecting points are reduced, right? Okay. You have this large pulse here and some slower pulses here, right? So these intersecting points are reduced, right? That means the switching frequency is reduced, right? Agree? The switching frequency of the inverter is reduced, right? So all the harmonic spectrum is based on the switching frequency of the inverter, right? Okay. So we have these intersecting points are reduced or the pulses are reduced. So therefore, obviously, it will induce or it will alter the harmonic spectrum. The resultant is lower order harmonics. Agree?
Yes, sir.
Clear? Okay.
Yes, sir.
So here, why we are getting, see, in case of unipolar and bipolar, the effective switching frequency is doubled, right? That means it will producing more number of pulses in the output voltage. So therefore, the harmonic spectrum is means that MF corresponding MF order harmonic are removed, right? Or it will completely eliminated, right? So here, the pulses is reduced, right? Okay, because of lesser intersecting points, the pulses are reduced. So therefore, so it will obviously present some lower order harmonics, right? Okay. So here, so this is the graph between the corresponding to MA, right? And this is output voltage RMS value, right? Output voltage RMS value. So this RMS value, output voltage RMS value, this is per unit. So I divide with this VS, right? This is per unit output voltage RMS value. So that means I divided with the DC source voltage, right? Okay, clear? So somewhere you have this. So this is corresponding to 0.1. So this is corresponding to 1. So modulation index is 1. So up to this point, the curve is linear. This curve is linear. So that means this is under modulation. This is under modulation, right? So the corresponding value for this one is 0.612 or 61.2%. Okay, so this is with sine PWM. So if you keep on increasing that, right, if you keep on increasing this MA, so it will go to nonlinear region, right? At some point of time, this is nonlinear region. At some point of time, its value is saturated, right? Its value is saturated. Clear? So you have this under modulation and this is over modulation, right? And after that, right, so here it will not make any intersecting operation, so just simply a square wave operation, right? So this is just simply a square wave operation. Clear? So previous one, what is the square wave output voltage? It is, we derived, right? What is the output voltage? Square wave RMS value. We
4
derived
Vs
from
minus 9 Vs.
0.78 times Vs, right? We derived this, right? That is the RMS value, that is the maximum output voltage anyone can obtain from a three-phase inverter output voltage, right? So this is corresponding to square wave, right? So this is 0.78. Clear? Or 78%. Clear? So that means when the inverter is operating in a square wave, right? The inverter is operating in a square wave, so that we discussed, right? So this is the square wave operation, right? So I think we discussed here. Somewhere we discussed. Okay, maybe another sheet. Okay, we discussed this, right? In inverter is operating in a square wave, the output voltage is 78% of Vs or 0.78 times Vs, right? So when the inverter is operating in sine PWM, right, with MA equal to 1, the maximum output voltage that you obtained is 61.2% of Vs. Okay, in other words, 0.612 times Vs. Clear? It's clear? From 0. When MA vary from 0 to 1, so output voltage RMS value vary from 0 to 0.612 times Vs. So this relation is linear, right? This relation is linear. When MA vary from 0 to 1, the output voltage, that is line, it is vary from 0 to 0.61 to Vs. This relation is linear. So this is linear relation. So once it crosses 1, right, so obviously that intersecting points will changes. So therefore the inverter will go to nonlinear region, right? So that means when MA increases to 1, right, after that, so it will go to nonlinear region, right? At some point of time, the maximum voltage, it can reach the maximum voltage, so that is 0.78 times Vs. Okay, that is the maximum voltage. So after that, even if you increase the MA, so there is no change in the output voltage, right? So this is normally, for example, this MA, so this is corresponding to 3.24, right? So this is corresponding to MF equal to FCR 758, or in other words, this MF corresponding to MF equal to 15, right? So this is some example. If MF, if we consider MF is 15, right? So here to operate the inverter in square wave, so that means we can go up to 3.24, right? 3.24, you can go up to 3.24, so that the inverter, after that the inverter will operate in a square wave. Okay, so you need to remember this 0.612 times Vs, right? So you need to remember that 0.612 times Vs. Okay, so many competitive exams, so these questions will ask, right? It's clear? So inverter, based on the modulation index, it will operate in 3 modes under modulation. So that is MA 0 to 1, MA 0 to 1. So over modulation 1 to, so that's just the limit of square wave, and after that square wave operation, right? After that square wave operation. So once you increase the MA, so there is no change in the output. And remember that from 0 to 1, so it will operate in linear mode. 0 to 1, it is operating in linear mode. So that is 0 to, means your output voltage vary from 0 to 0.612 times Vs, right? So now the question is, you're designing a 3-phase 415 volts inverter, right? 3-phase, what should be the value of Vs, right? What should be the value of Vs when the inverter is operating in sine PWM mode? When the inverter is operating in sine PWM mode, what should be the value of Vs? So that is Vs by 0.612. Okay, you need to select a Vs, right? Sorry, not Vs. Output voltage RMS value by 0.612. Right. So earlier it is, if you want to operate in a square wave, right, it should be 0.78. So this Vs should be 0.78 times. Clear? The maximum voltage that we can obtain with sine PWM is 61.2% the DC voltage. So you have any doubts on this?
Sir, I have a small doubt, sir.
Yeah.
Sir, you said that from 0 to 1 of MA, it is a linear region under modulation.
Yeah. Mm.
So for value of MA value 1 output V0 should be also 100%, sir.
Mm-hmm. V0?
If we see graphically for x equal to 1, y also should be 1, sir.
Where it
Because
is x should be 1, y should be 1?
X coordinates are MA is 1.
Oh, MA is 1, right? Yeah.
Then as it is a linear line, then y also should be similar magnitude.
No. The meaning is it will follow some y equal to mx curve, right? Okay. But it will follow some y equal to mx. It should not be like that, right? So linear may be, it may be like this, it may be like this, it may be like this, right? All are linear curves only, right? So it is
Okay,
having
sir.
some certain slope, right? Okay.
Understood.
Okay, that is mean that if it is 1 means it should be 1 here. Okay.
Okay,
Yeah.
sir.
So what is the reason of this bending, sir?
Mm-hmm. It's non-linear, right? This one? This is your doubt? Someone has asked some question. What is the reason for?
Bending, sir. The curve is got bent after.
That is non-linear, right? So this is non-linear. This is the one you're asking, right? Yeah.
Reason for this non-linearity?
Because in non-linear, the intersecting points are completely changed, right? Okay. So earlier, you know that at what point that intersecting points are happening, right? Okay. You know the width of the curve and all those other things, right? So once that intersecting points are changed or some intersecting points are discarded, right? So obviously you don't know, you don't have control on the inverter, right? So that means output voltage changes. Okay.
Okay.
You have any other doubts on this? Okay, we'll move to the other one, other topic. Right. All these questions are whatever we discussed so far, right? So these are very, very important in all the competitive exams, right? Yeah.
Sir, I have a doubt.
Yeah.
Sir, in PWM scheme, how to select the region of operation? Like we have to select MA value under modulation or over modulation, because
See, normally we operate all the time in under modulation. Okay, when we are designing an inverter, so we are make sure that it is operating between 0 to 1, right? Okay, we are make sure that that is operating from 0 to 1, right? In certain cases, for example, if it is driving an induction motor, right? For example, suddenly there is a slight increase in the load, right? Or increasing the load beyond what you are actually designed, right? So in that case, you slightly go for over modulation, right? Okay, in that case, you slightly go for over modulation, right? So therefore, these over modulation is normally required. Okay, so when you're designing an inverter, we have to make sure that it should be operating this under modulation only. Okay, clear?
Yes, sir. Thank you, sir.
So next we'll go to zero sequence injection PWM. Zero sequence injection PWM. So one thing you have to notice that, right, in this PWM, right, so whatever the curve RMS value that is you are obtained, right, so that modulating signal, so both are same. Okay, that means, so here the output voltage V0 RMS, right, so that is V, that is related to this MA. So this is MA sine omega t. So this is per unit value. The per unit value of this RMS voltage is related to this MA sine omega t, right? Okay. If you want to change the MA value, so obviously the modulating signal is changes, right? So both are in per unit relation, because here the MA is changing from +1 to -1, right? So therefore, this V0 RMS value is also changes from in per unit +1 to -1. Clear? So now the zero sequence injection PWM, right? So the drawback with over modulation is, what is the drawback? The output voltage is increased, but the drawback is lower order harmonics, right? The drawback is lower order harmonic because it is missing some intersecting points, So we have this zero sequence voltage injection PWM, right? So here, this is the actual waveform, right? So this is the limit, right? But this waveform is exceeded here, right? Okay, you notice that? If you notice that this waveform is exceeded, right? Okay, this VM1, this waveform, this is the actual modulating signal, so that is exceeded. So that means that is operating in over modulation, right? With over modulation, some of the some of the switching we lost, right? So here we are added a zero sequence component to this one, right? We added a third order harmonic to this waveform, right? So that means we have this modulating signal, so that is original, plus V modulating signal, so that is third order harmonic, right? Okay, we have added this third order harmonic, so this is the resultant, right? If we add this one, so this is our resultant waveform. Okay, this is our resultant waveform. Clear? If you notice that the resultant waveform, so that is under the, if we assume this is +1 limit and this is -1 limit, right? So here in first case, the actual modulating signal, the output voltage is increased, right? Means the voltage is increased, means it is greater than +1, right? So the resultant waveform, so that what we obtain is less than 1, right? Agree?
Yes, sir.
It's clear? Right? It's clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So here, that means the output voltage, the waveform is remained same, but so if you notice that, so this is the area that we lost, right? So this is the area we lost, right? When you're increasing this third order harmonic, so this is the area we lost, but the area that we gain is, so this one. Okay. Similarly, so here also in the negative half cycle, I will draw. So this is the area we lost. Okay. The peak value is reduced. The resultant, when you are adding after zero sequence, right, the peak value is reduced, right? So therefore some reduction in the output voltage, so but it is gained here, right? So that means that shoulders are widened, right? Now the waveform shoulders are widened, so that means if the originally, if this is the output voltage you are getting, right? So when this waveform is widened, so that means it slightly increases, right? Agree? It's clear? It's clear?
Yes, sir.
Yes, sir.
Right. The output voltage or intersecting points, if it is widened, right? So that means it slightly increases.
Sir, is it a healthy move to induce zero sequence?
Yeah, we'll discuss that. Okay, we'll discuss.
Okay.
Clear? We are injecting some third order harmonic. It may be triplet harmonic. We can induce any order harmonic. It may be third order harmonic, or it may be sixth order harmonic, or ninth order, or any other harmonic. So we can induce that, right? So that we have to make sure that the resultant waveform should not exceed +1 or +1, or it should not exceed, or it should not go into overmodulation, right? Clear? So when you are injecting this third order harmonic, right? So these third order harmonics will present in the phase voltage, right? But actually in the line voltages, these third order harmonics becomes eliminated. Okay? Clear? These third order harmonics are present in the phase voltage, but they are actually eliminated in the line voltage.
Okay, sir. Clear.
Okay. So that means the simple thing, right? You can easily derive this one. So we have this original modulating signal, something like this VM, sorry, it's MA1 sine omega t is the original modulating signal, and this is MA2 sine omega 3 omega t, right? So this is the zero sequence order harmonic. So this is the resultant. Okay, this MA1 sine omega t plus MA2 sine 3 omega t. This is third order harmonic, right? So you have another one, MA1 sine omega t minus 120 degrees. This is for B phase, plus MA2 sine, right, 3 omega t minus 120 degrees. Okay, minus, right. So this is A phase modulating signal, and this is B phase modulating signal. Similarly, you have the C phase modulating signal, right? Similarly, you have the C phase modulating signal. So line voltage is the difference between these two phases, right? So that means when you do V mod minus VB modulating signal, right? So obviously these two, this zero sequence, so here and here, so both will be cancelled. Okay, when you subtract these two waveforms, right, the zero sequence order means this zero sequence voltage is get cancelled. So that means line voltages are free from the zero sequence harmonics. Okay, so that only present in the line phase voltage, but it will not exist in the line voltage. Clear? Okay, so by using zero sequence injection PWM, we can actually increase the line voltage RMS value, right? But the advantage here, so this is what we obtain with zero sequence PWM. Okay, so here compared to this previous one, so these pulses are slightly widened. So therefore output voltage is slightly increased, and it will almost reduce the lower order harmonic, or it will, right, so it will reduce the lower order harmonics. Okay, so you have two ways to increase the output voltage beyond 0.612 Vs, that is the maximum voltage that is obtained, right? So one is going over modulation, the other one is zero sequence voltage injection PWM, right? In case of over modulation, so the drawback is it will induce lower order harmonics. In case of zero sequence voltage, so that means it will not induce any, lower order harmonics. It's clear? Right. So by using this zero sequence, right, you can go up to 0.707 times Vs. Okay. The output voltage VAB RMS value, so can we go up to 0.707 times or 70.7 times Vs. Clear? Actually, we need to remember 3 digits. One is 0.78 Vs. So this is the output voltage RMS value when the waveform is operated in square wave. Clear? That is the maximum output voltage, so that can be obtained from the inverter. Clear? And the second one is 0.612 times Vs. 0.612 times Vs. So this is the output voltage RMS value corresponding to MA equal to 1. That is maximum output voltage. So that is obtained with sine PWM technique without going for over modulation. That is MA equal to 1. Right. So this 0.707 Vs. So this is the maximum voltage. Right. So that is obtained with zero sequence injection PWM. So without the problem of lower order harmonics. Clear? So here the boost in output voltage, so that is 15.6%. Okay, by using this zero sequence voltage injection, so we can increase the output voltage to 15.6% from 0.61 to 0.707 Vs. Clear? Clear? So this is actually known as DC bus or DC voltage utilization, or DC bus voltage, or DC bus or DC voltage utilization, right? So that means in case of this one, this is 78%, right? Or it may be 61.2%, or it may be 70.7%. So this is normally known as DC bus utilization. Okay, so how much DC voltage you are inputting, so what is the maximum voltage you are getting on the AC side, right? See. Okay, you have any doubts on this? Your doubts on this?
Sir, in this system, third order harmonics, if we are adding, it will not create any problem on the system?
That I discussed, right? So the third order harmonic only present in the phase voltages, that will not present in the line voltages. It will automatically cancelled, right? When you're subtracting A phase and B phase, right? So that means it is automatically cancelled. Okay. See here, we discussed it, right? See here. So here A phase modulating signal, this is A phase modulating signal, and this is B phase modulating signal. So when you're doing A phase minus B phase, you will actually get the line voltage, right? So that means in line voltage, this harmonics will not appear. It will only appear in the phase voltages. Okay. Anyway, we are not interested in phase, and it will circulate in phase voltages only.
Okay, sir.
Sir,
Yeah.
is it 3 omega t minus 360 degrees for VB?
I think this is 3 omega t minus 120 degrees. Okay, I'm not sure. I don't remember.
With the 3 common, okay, it is correct.
3 common. Should be 3 common.
Yeah, I think 3 common. Okay.
Then if you cancel, then both will cancel. VA and VB if you take difference.
Yeah, it will be cancelled. I think this 3 omega t minus 120 degrees. I think this is correct, right?
Yes, sir. Second.
Yes, sir. Yes, sir. 3 omega t minus 120 degree.
Okay.
Sir, the zero voltage injection process exactly I'm not getting.
Mm-hmm.
How do we do this? Zero voltage injection.
Simple, right? You have you know that MA you're operating with 1.2. Okay, right? Somehow you're operating a motor, right? Some motor drive or induction motor drive. So you know that you're supposed to operate with MA equal to 1.2. Okay.
Yes.
The straight away if you are increasing or if you're going this MA to 1.2, right? So this is corresponding to 1. So this is 1.2, right? So that means you observe that. So there will be some lower order harmonics, right? Okay.
Yes,
so now you need to write some algorithm. So here, if you want to make the same output voltage, whatever you are getting, right? And you need to calculate how much zero sequence voltage you need to inject in this waveform so that this waveform will be in the this waveform is within the limits of plus or minus 1. Okay.
Okay, sir.
Yeah.
Okay.
Right. So you have to do some alga. Means you have to write some lookup table or something like that, right? So based on that, it will pick up the value of magnitude for the zero sequence injection magnitude. Okay. So you have any doubts on this?
Sir, actually, how is this zero sequence voltage injected, sir?
It's not see here we are just adding. So earlier we have the sine omega t, right? So normally we are generating only MA sine omega t, right? So instead of that MA sine omega t, we are adding one more. So simple. Okay. See here how normally we'll do PWM. Okay, in simulation you have this sine wave, right? Okay, clear?
Yes, sir.
And you will generate this carrier. So this is triangle carrier. So you need to compare these two, right?
Yes, sir.
Okay, so this will generate switch S1 and the inverted one will generate switch S4. That's it, right? Okay.
Yes, sir. Yes, sir.
This is how normally we'll generate a sine PWM, right? Okay.
Yes, sir.
See, in case of zero sequence, right? So with that, you just add some zero sequence component. So this is omega and this is 3 omega.
Okay,
That's
sir.
it.
Okay, sir. Okay, sir.
Okay.
Yes, sir.
So you need to add this one in all phases.
Three phases, all the three phases. Okay, sir.
Right. So if you have doubt on this one, right? So when you are adding zero sequence components, that means A phase modulating signal, B phase modulating signal, VA, VB, and VC modulating signal. If you add all these modulating signals, you must get 0. Okay, so then only you are appropriately added the zero sequence. Okay.
Yes, sir.
Clear?
Yes, sir.
You have any doubts on this?
Sir,
Yeah.
isn't zero sequence related to fundamental frequency component?
Zero sequence are not fundamental frequency, no? It has
Means
some.
third harmonic and zero sequence have similar properties, but
No.
zero
Zero sequence harmonics or triplet harmonics, right? All are
triplet
same. Okay. Triplet harmonic or zero sequence harmonic both are same. Okay. There is
harmonics
other.
is multiple frequency component, whereas zero sequence is a fundamental frequency component which we do in fault analysis.
No, sir. The meaning is zero sequence and fundamental triplet harmonic both are same only. Okay. So both are rotated at the same point.
Yes, properties are similar, but
Properties, they're similar, not similar, they're identical. Okay, the other name for triplet harmonics are zero sequence harmonics. Okay.
okay.
This both are same. The wording is different. Zero sequence or triplet both are same.
Yes.
Are identical. Power system you might have studied, right? Positive sequence, negative sequence, and zero sequence.
Yes, sir. But during fault analysis, which we take, they are related to fundamental frequency components only. Thus, each phase unbalanced currents or voltages we divide into sequence components. Fundamental.
Okay. Okay, so here zero sequence and triplet both are same.
Okay.
Yeah, any questions on this?
Sir?
Yeah.
In synchronous PWM and asynchronous PWM, in case of unipolar, are the number of pulses created same or different?
See, in case of unipolar, that synchronous and asynchronous concept will not come, right? Okay. So normally, in case of three phase, when you have three modulating signals, then only this problem will come,
Okay.
right?
Yes.
Okay. So here, in case of bipolar or unipolar, right, you have only one modulating signal and one carrier signal in bipolar, right? So obviously, they both are synchronized. Okay.
Yes.
In case of unipolar, you have one modulating signal and two carriers, right? And carriers are in opposite direction. Okay, you can't change that, right? Obviously, it is synchronized.
Okay.
Okay.
Yes. Thank you.
Have any other questions? Have any other questions? Yeah. You have any questions? Okay, I'll stop here. Someone who recorded that, please stop it. Otherwise, it will record until the last person leaves.